I'm really more on the analytical chemistry side than the nutrition side. And the metabolomics is a relatively new focus of mine. So this talk is going to be less about outcomes, but more about how this kit worked in our validation effort. So introduction, just real quick about how we got to metabolomics, for mostly targeted metabolomics, and then focusing also on the Quant 500 assay with our validation efforts and a feasibility study, which is a very, very small sample size. So my mantra when anyone's talking to me about human milk analyses is human milk is not plasma. You can also turn it around. Plasma is not milk. As you can see here, the relative amounts of protein, fat, and sugar, so the macronutrients, are very different in milk. You have a lot more sugar, you have a lot more fat, and that will interfere with your analysis. So most likely, whatever you've set up for plasma, what you want to now analyze in milk, is not going to just work nicely because you want to. You do have to put more effort into method development and so on and so forth. So besides the matrix interferences you have to deal with when you analyze human milk, there's also, as Theodore already mentioned, the concentration differences or the vast, huge differences in concentration within milk, but also compared to, for instance, plasma. To your right here, you see we analyze some water-soluble choline forms and some other related metabolites, and anything that is highlighted or in black font has very different concentrations in milk than plasma. And you want to make sure that, of course, everything is in your linear range for your detection. So there are things to consider that most likely any kind of method won't work just because it works in plasma doesn't mean it works just like that in milk. So you will have to do some adaptations to make it happen for you. So our interest in the targeted metabolomics started actually with the IDQ P180 plate for milk. We got funded to create new reference values for human milk micronutrients, as micronutrients is our actual expertise more than metabolomics, I have to admit. So the milk study is the mother-infant lactation quality study. We collected longitudinal samples up to 8.5 months. And again, mostly we were interested in micronutrients, but since we're collecting that many samples in 4 different countries, we also wanted to include additional analyses. So we collected other matrices as well. So we have blood samples, stool, urine, anything we could think of. And of course, we wanted to include other analyses than just micronutrients. And one of them was metabolomics, starting basically from, hey, we want to analyze amino acids. And then if you go down that road, you ended up with targeted metabolomics, which made a lot of sense to us. So we approached biocrates about a validation to see if human milk would actually be useful and a valid matrix for their commercial available kits. And as Terry also already mentioned, there are some adaptations you have to do with internal standards. You have to adapt your acquisition method and so on and so forth. But overall, and as already mentioned, it was published in 2019, our outcome of this validation effort with biocrates. We found that it was well worth using the kit. It was giving us good results and reliable results. And as mentioned, we had a small sample size for just a feasibility study on that validation plate, which was done in Innsbruck in Austria, as they know the kit a lot better than we do. And we found in the milk from Bangladeshi mothers in this little feasibility study that if you're quote unquote a healthy mother, meaning the BMI was greater than 18.5, we had higher concentration in some of the amino acids and biogenic amines and lower concentration in some of the lipid species compared to milk from mothers with stunted infants. It's great to see some differences in such a small sample size, but we were actually more confident in our results given the small sample size that we found the same trend than Semba et al. Found in their publication and research in Malawi using the very same kit, but analyzing actually serum from stunted versus non-stunted children. So it's nice to see. We were quite excited about it, that we could basically replicate these results using a proxy, a milk, instead of an actual blood sample from an infant. So with that, it was even more confident in our results and that the kits are useful for human milk applications. So now in 2019, I think the MxP Quant 500 assay was available finally. We were, of course, not ready yet to analyze anything given just the size of the study. Samples need to be collected. This was a study started from scratch. So Fadi mentioned that there's a new kit coming out, and now we're including those triglycerides, which is extremely attractive. As you all know, probably that the human milk, as we just discussed, the lipid fraction is far most comprised of triglycerides. Also, some free fatty acids are now targeted in this kit as well. And our interest was also into EPA, AA, and DHA. So you can check mark this with the kit. And again, it's a very comprehensive coverage of those 630 metabolites versus 188 from the P180 kit. You just use one analytical platform. You need a little small, like just one sample, very small, simple volume, and you get so many data points for which you would have to create so many different methods, much more simple volume and time and money. So it just makes sense to see, hey, can we use this kit as well? So we did the same approach. The Innsbruck team did the actual feasibility/validation in-house, following their own protocol, so we can make sure everything is being done the same way as they would do with any other matrix. And again, this is one 96-well plate. And on that plate, we have, again, these 25 slots available for an individual milk sample set. So this time we had in-house available sample set from Brazilian mothers, which I'm going to talk about it later. The project outline is as given here. I cannot talk about everything. I wasn't really there to do the validation, I have to admit. It would have been quite interesting to me. But it's basically the same project outline as the one we would have with the P180. So we're going to focus here on how the concentration and linearity worked out, inter-day variations, overall metabolite recovery, and then I want to talk a little bit of outcome of this feasibility study. And yes, it was published finally in 2025 in Metabolics. So for concentration linearity, used 5 different simple volumes for the milk. 2 microliters to 20 microliters is given here. And then the Phi analysis was also done in 2 different ways. One was a 1:50 dilution and the 1:20 dilution. And you can see the blue font highlights the typically used dilutions and sample volumes when you use the kit. So for concentration, I just wanted to see which of these parameters or conditions will give me the most usable results. And for linearity, we looked into the concentrations obtained for the metabolites across these 2 to 20 microliter sample volumes used, adjust the sample volumes by the quote-unquote dilution factor, and then see how they compare to each other. And for the concentration, it's nice to see that I like that very much, that we can still use the typically used conditions of 10 microliters and 1:50 dilution. I don't have much here for the Phi analysis, but the 1:20 dilution didn't give you any more results, but it will give you more matrix. And the one mantra as well is that we want to have the least amount of matrix present in any kind of mass spec analysis if possible. So there was no point of using only a 1:20 dilution. If I can get rid of more matrix and getting the same results, will keep your mass spec a lot happier. And here in little tables, I have them throughout my talk for the validation, a little bit of breakdown, how we ended up to get to the results. And as you can see here, for the different sample volumes used, you can see the metabolite number that was not detected. So you can see at 2 microliters, we have 124 that were in there. We have some also that were still providing some sort of data, but it was very uncertain as it was below the limit of detection. So overall, you can see at the very low sample volumes used, we have a lot of data that is lost that we can actually look at when we use the other 3 sample volumes. And then from that, we can see that the 10 microliters give us the most result with 506 metabolites. If we now look at linearity, we distinguish between the LCMS and the Phi metabolites to see how close the concentrations are from the different sample volumes. You use 20% cutoff for CB and 30% cutoff, given that the LCMS metabolites have a standard curve and a bit better if you want to think about it. They have a bit more, I think, a robust quantitation. The FIA will have the internal standards, it's just fine, but we were fine giving them a little bit more leeway. So we did that. We look into how close the relationship were between those different sample volumes. We ended up with over 95% of our metabolites that they're linear. So again, a little breakdown here, just to show you, we have a certain number of metabolites. I just counted whatever I can to have the biggest pool available and then see where things fade out. So if you just do a quick superficial, like, okay, here are our cutoffs, 20 and 30%. What are we losing? So we lost about 9 metabolites for LCMS and 37 for FIA. Within there, of course, given my parameter given up here, I already have included metabolites that were below LOD. So there are some below LOD and have an unacceptable CV for linearity. But then if you think about how many metabolites we lost at the low end of our sample volumes, if we exclude those, we noticed a bunch of the triglycerides that were previously not accepted within the CV are now within the CV. So it's always worth looking into a little bit more closely into your data to see what is actually possible. Given that 2 or 5 microliter sample volume was not the one we want to use anyway, we can confidently say that those of 24 triglycerides and some of these 3 LCMS metabolites are also linear, which ended up giving us this number. I also want to point out matrix interferences we noticed, and one example is the palmitic acid, which is one of the main free fatty acids in milk as well. And you can see the data we got here. So you can see at the low end, we don't even get any results. At the high end, we have a number, but it is not reliable as it is below the LOD. And then we have 2 valid numbers up here. But you can see, given the sample volume and the concentrations measured, there is a trend. However, it shows you also that the matrix most likely interferes with the detection of this fatty acid. And between 10 and 50 microliters, we do not have that interference. And if you just look at these 2 numbers, you're still within a nice linear range. But you got to consider we only looked at 2 of the used sample volumes here. So I would like a little bit more data around this to see whether or not this is a trend. But it certainly shows you nicely how the matrix can interfere with your detection. So next was inter and interday variation. Intraday variation, very simply, we just analyzed 6 replicates of our human milk pool. And we want the CV smaller than 20% of our results. And I included all the data that was available for each metabolite, as long as there was data above LOD for 4 or more replicates. And you can see the breakdown here again. We have about 90% of our metabolites within our acceptable CV range for intraday variation. But if you actually look at the breakdown up here, this is what we detected. This is was fine. This is what was above. So 45 metabolites were above 20%, but then you can see the vast majority of that was between 20 to 30%, and only 4 were above 30%, and even there were below 40%. So overall, nothing was like it's an extreme outlier in the intraday variation approach here. You can see those 4 metabolites were basically lipids. So triglyceride, ceramide, and phospholipid, 2 of them. But overall, I think that is a really good result for intraday variation, given how many metabolites you want to analyze with this kit. For interday variation, we used the 25 individual milk samples from the Brazilian mothers, and they were analyzed on 2 different days, and we checked the ratio of the results. So cutoffs were chosen as follows. We have a good ratio if we have a 70 to 130%. Suboptimal, unacceptable ratios are given here as well. So my little breakdown here is I looked at interday variation, and given of how we did it, we basically have 25 ratios. If all metabolites are present in each of those 25 samples, would make 25 ratios for each metabolite. So to look at it, just to give a quick overview here, I said, okay, so a minimum of 50% of the samples, so at least 13% of the samples, the metabolite needs to be in one of those categories to be counted here. And as you can see, most of them were good, some are not so good, and some are really not great. And if you look overall, if you can look into metabolite classes to see if there's a trend of some, and you can see that there was a reduction in concentration. We look at the fatty acids, the di and triglycerides, and more an increasing of acylcarnitine ceramides and the lyso or phospholipids. There was a cluster around the unacceptable values. There were a lot of the lyso PCs that were not in an acceptable range, not even suboptimal. So it's good to see how your metabolites behave over time, so you can make informed decisions of what you can use and what you cannot use very well. So the last slide for the validation is our recovery accuracy, which for me is usually the most attractive one, just to see how things after all behave. For this effort, we had the neat human milk pool analyzed and a diluted written 1:2 and 1:5, but we also did a spiked human milk, actually 3 different spikes, and each was analyzed 6 times. We would have preferred a recovery between 80 to 120%, and then preferably also a CV of our replicates within our 20%, which is like commonly used for us. I should mention the spiked version of our milk was spiked with the plasma QC that you usually get with your kits, so QC 1, 2, and 3. We had a discussion with the team in Innsbruck about it. Since they didn't have all the standards available for the kit, we opted to use the plasma samples as they have known concentration for each of the metabolites I analyzed with this. If you now use your matrix and you spike it with another matrix with a given concentration, we come back to the concentration differences between the two matrices I mentioned in the beginning. So now we can't control how much we spike in the sense of you have a given concentration in each of the plasma samples, meaning if you have a metabolite that is highly abundant in the milk, but also highly abundant in plasma, you may see a spike, but you also have a high possibility to run into detection limits and saturation effects that you may not get a good result. You could also have a really high abundant metabolite in the milk and a really not abundant or very trace abundant concentrations in the plasma, which would also not give you any recovery results, since the little bit that you add from the plasma will not make a difference in the concentration. And then you could have a metabolite that is not really present in the milk, but present in the plasma, which is actually nice because then you get kind of an idea how that metabolite is recovered overall, given that we used one human milk pool. But as Terry already mentioned, there are many different influences also what could change your metabolite profile in the milk. So you might have these metabolites present in a different milk. So it's nice to see that we could get some recovery ideas about that too. So if you now look at this overall, this is a violent plot, and I had collapsed some of the metabolite classes just to get a better overview. We look at the recovery for whatever we got from all of our results here. And we look at amino acids and related compounds, acylcarnitines, bile acids, biogenic amines, carboxylic acid, cholesterol esters, the ceramides, triglycerides, fatty acids, the phospholipids. Others are like the hormones and the indoles and the amino oxides, like the ones where we had very little metabolites within class, and then the triglycerides at the end. And overall, you can see the recoveries were pretty good. If you look at the median bar here, it's around the 100% recovery we were hoping for. The red dotted lines are indicating the 80 to 100% recovery, and then the dotted black line down here is 20% for the CV. So you see the CVs are given here in the Radlin graph and the recoveries there. The one I want to highlight are the cholesterol esters, as overall the recovery was lower for those than for other metabolite classes as shown here, and we were closer to 80% in median compared to closer to 100% for mostly all of the other ones. However, as you can also see, the recoveries were quite reproducible. So as long as I get good CVs, I was okay with the recovery rate, but it's good to know how they behave so you can adjust accordingly if you want to do an absolute quantification. And of course, with this amount of metabolites, we have some that are not quite within this range, but the vast majority, other than cholesterol esters, you can see for each of them are within our 80 to 120%. So now our feasibility study, as mentioned, we had samples we were allowed to use from Brazil, and the mothers provided samples at multiple time points, so at least 2. I tried for 3, but it was not even possible for the little sample numbers for each of these time frames. So group A was sampled from colostrum to transitional milk the first week. Group B is about 1 to 2 months, and group C is about 3 to 4 months. So we have 2 more mature milk sample ranges and 1 very early on. And to show you the data to make any kind of sense, I opted for a kind of a volcano plot. So we're looking at the significant differences on the x-axis, and then the concentration changes on the y-axis, and anything that is highlighted with yellow is your significant difference range up to the 0.05 that is usually used for cutoff for significance. Also divided the metabolites a bit to make it a bit more visibly appealing to actually be able to see something. As you can see here, we have the triglycerides, diglycerides, and a bunch of the different ceramides up in this graph. And we could have 3 different graphs in each, and we could compare it group B to group A, group C to group A. So that's the further along sample, and then also the 2 mature milks to each other. And down here, we look at the amino acids, biogenic amines, and related acyl carnitine sphingomyelins in the yellow, the cholesterol esters, the phospholipids, lysophospholipid, fatty acids, and carboxylic acids, and then again, those trace metabolites, again, where we have not many responses within class of those very little ones that didn't have many metabolites within class, again, endos, hormones, so on and so forth. So it's a longitudinal approach here just to see how changes occur. And as you can see, a lot of purple is significantly changing and reducing over time. So we had triglycerides, also some of the ceramides, some of the cholesterol esters down here, and phospholipids that were lowered in concentration the further we went into the lactation stages. We could also see that the amino acids increase and biogenic amines are related, certainly also quite off between the 2 later stages, and certainly to the 3 to 4 months to both of those earlier group A and group B samples. And then we also looked into the literature to see if we find any longitudinal data just to compare our data to see if we are in agreement with the other data. And you should know and remember that we use the MxP plate, and the other person who used it is Terry. So it's the only direct comparison with the same method. Everything else is probably LCMS based. Some would be GCMS, I think, and of course NMR based. Metabolomics were also published. So we're comparing in terms of methodology, some apples to pears, but overall it was nice to see that we could also find that the glutamine and glutamic acid as the 2 amino acids that are always reported to be higher later in lactation. We found the same outcome here. And we also mentioned already the decrease in phospholipids, as you can see down here, and also here, not so much in the later stage of lactation. And we also found that the triglycerides, the free fatty acids, the amino acids, and the sugar are the top 4 most abundant metabolite classes. And I think that was actually Terry's study. So overall, I'd say we were happy that this assay was successfully adapted to human milk, and that we found comparable results to the literature, which just helps to ensure or makes us even feel better about the results we have. What we really like is that we can use the same assay for milk and blood, because we are really looking into mother-milk-infant relationships in our laboratory here. And I'm always happy if we can use the same method. It would always be good to have a human milk quality control that you can run with each plate. If you have one that you know the concentration of at this point, as it's always better if you have that matrix match QC than just the plasma QC. I would recommend to run both. For outlook for us, we have from the milk study already collaborated with biocrates to run 800 samples. We have an omics subset within our study, so we have 200 samples from each country, and they're spread out between 1 to 8.5 months of lactation. So we have a bunch of longitudinal data we have to look at, we haven't done yet. We will also have corresponding plasma samples, and they will be analyzed hopefully in the summer. And then we can also have connect all that data in a big machine learning approach, which is also underway with other available omics data, anthropometry, micronutrient data, of course. And there's a lot to do and so little time. But thank you for your attention. I know I went a little bit over, and I'm happy to try to answer any of your questions. Thanks.